Hello and welcome to Lecture 20, where we're going to discuss the final section of Chapter 6 on the most difficult type of collision and the most mathematically complex type of problem that involves conservation of translational momentum. Conservation of momentum. Okay? So here we go, right? They're algebraically kind of tricky, but let's talk about how we do these types of problems. Right? I have a few interesting examples. So this type of problem is called a glancing collision. I'll define what that is. So let's get into it. All right? So a glancing collision is any collision that is not a head-on collision. And if you need to review what a collision is and why we expect momentum to be conserved in a collision, check out lecture 19. Okay? But anyway, so it's any collision that is not head-on. All right? So the centers of the objects are not lined up. Okay? So it occurs when either the velocities or the centers of the colliding objects are not aligned. So you could have objects that are lined up, but then their velocities are off kilter, or you could have both their velocities and centers not lined up, and so on. Okay, but that's the idea, and the reason that this matters is that means that it's very much a two-dimensional type of problem. It's 2D through and through. Maybe, the objects to begin with were 2D, moving in different directions, with X and Y components, or maybe just only after the collision are the velocities, have X and Y components and are really 2D. But it doesn't matter. The important thing is that something about this problem is 2D, which means you have to consider momentum in X and Y. And that's the whole deal here. It's all about momentum and X and Y. All right? They can be all the typical types of collisions, the big three: elastic, partially inelastic, and perfectly inelastic. So we're going to see all three types. And this type of collision always requires momentum conservation in two axes. So that's really the approach we're going to see over and over again. All right? And that means that we'll always be looking at these two equations. In every single one of the examples I have in this set of lecture notes, it involves these two equations. All right? The notation might vary a little bit between the problems. I'm using here in the key formulas the notation where px1 would be the initial momentum in the x direction of object 1, and then px1 prime would be the final momentum in the x direction of object 1, and then so on for object 2, and then the same thing in the y direction, okay? And these are components, all right? And they're component vectors, and then we can also write them as just components as well, all right? So we could change these vectors, into, their appropriate cosine and sine, relative to some given angle. Okay? All right? Furthermore, all right, and this is true for all the collisions, and then furthermore, for elastic collisions only, excuse me, we also have conservation of kinetic energy. And there, since kinetic energy is a scalar, it's much easier to work with. There's no such thing as x and y of kinetic energy, right? There's just kinetic energy, right? The whole deal is it's the magnitude of the velocity squared. And so each one of these kinetic energies, by the way, would always have the form 1/2, this would be m1 v1 initial squared. Okay? All right? And I suppose, right, if you're thinking, wait, notation, I suppose I could have used the prime notation here since I did use that notation up above. Okay? But here I'm identifying them as initial and final kinetic energies. All right? Because I didn't have to worry about a triple subscript, so it's just kind of easy to put the initial and final. Hopefully that's clear. All right, initial, final energy. And again, we're only ever going to consider energy for really the elastic collisions, or for partially inelastic if the energy is specified. Like if we're told, half the energy is conserved or something, then we can use a version of this equation. Okay. All right. There's three types of problems. We have glancing collisions that are inelastic, glancing collisions that are partially inelastic, and then the most complex, glancing collisions that are elastic. And I'm sorry, I left the word elastic out. I was just typing this up, and it's very important, but I left it out. So type 3 are complex problems that involve glancing elastic collisions. And it is always interesting that elastic is inherently the most complex. But of course it is, because it's the only one that would have three equations to start with. So these are three, to use a mathematical term, independent equations. All right? And together, that means you can have up to three unknowns, okay? And, right, I say that, up to three unknowns, whereas all the others are limited to two unknowns. Notice, right? We can solve up to two unknowns. And I don't always like call attention to the exact mathematical form of solving, but these problems are so structural, so just based on an algebraic system of equations that it's hard to really kind of move away from that. This is systems of equations applied to physics through and through. Okay, but let's get to those examples. All right, so we'll start with the simplest type, a perfectly inelastic collision. So we're going to have some initial momentum. Afterwards, there's only be one object, which makes this type of problem inherently easier because in this case, the two birds are moving as one object. And so, the approach, there's less to solve for, and we can find out what the final state is. All right. So let's see, we had a falcon here. We're given the mass of the falcon. We're given its initial velocity. We're given the angle that it's moving. So it's moving in X and Y, right? That's the 2D part. All right. It's going to crash into a pigeon with a known mass. All right. The pigeon also has a known initial velocity. So basically we know everything that starts the system, starts the collision. And then afterwards, we want to find the direction of the falcon with pigeon. So it's going to be the combined mass immediately after the impact. And then that's the speed and direction. So we want the magnitude of that VF and we want phi. And that's it. That's what we're solving for. Right? I even say right here, right? VF and phi. All right, so let's do it. So here we're going to start with our two momentum equations because I said every single problem I write out these two equations in some form or another. All right, and I'll just quickly run through them. So in the X direction, we have the falcon and the X component, the initial X component of the falcon, the pigeon and the initial velocity of the pigeon. Notice the pigeon doesn't have a component because the pigeon is entirely X. Afterwards, it's just going to be the combined mass and then the final velocity in the X component of the final velocity. All right. No subscript here because there's only one object, so all I need to write is that it's X. All right. And the prime here definitely represents final. Likewise, in the Y direction, there's just the falcon and it's a component. And then afterwards, total mass times the Y component of the final velocity. All right, so let's go ahead. We don't have to do any algebra. We can just solve for one at a time. So I'm going to find V final X. I'm sorry for being inconsistent. This is the same as Vx prime. Okay, these are the same. All right, but I switched my notation there. But anyway, so we plug in the numbers and we solve and we find 12 meters per second. All right, excellent. We do the same thing for Y. And the sign is going to show up as negative. That makes sense because the final velocity should have a negative component. All right, because the initial velocity was entirely negative. And where does the negative show up? Well, it just shows up because I took sine of negative 45. I mean, there's different approaches. I could have taken sine of 45 and then remembered to just denote it as negative since I know it's in the negative direction based on a coordinate system with X and Y. But whatever way you do need to acknowledge that it will be negative, okay? All right. And then we're going to find the overall magnitude of VF using the Pythagorean theorem, and it's 15 meters per second. All right, that makes sense that it should be smaller than the initial velocity of the falcon because now it's more massive, more inertia. All right, and plus the collision itself took away kinetic energy. Any perfectly inelastic collision takes away energy. And then we find our phi, and it's negative 37. All right, looks good. All right, and that also makes sense that it's less steep than 45 degrees because grabbing the bird that was moving in entirely the X direction means that the final combined velocity should be more X than the initial falcon velocity. Right? We should kind of have that added. Essentially, we're going to be doing like a tip-to-tail momentum here. Okay, these are velocity vectors, but essentially when you add them together, that's going to be the effect. So something like this. Okay, and that would be like P final as a vector. Okay. And actually, that's a good segue to a couple of concept questions that explicitly show that when it comes down to it, you can really always check the reasonableness of your answers by thinking about the momentum vectors. And remember, momentum vectors are always parallel to velocity vectors. There's different lengths. And sometimes if you have a very large mass or a very small mass, then the velocity vectors can change their relative length to each other. For example, if this pigeon was moving really fast, but it was very low mass, then its momentum vector might be a little small like that, parallel but small. Whereas if the falcon was moving slow but was really massive, it might have a longer length momentum vector because of its large mass. Okay? All right, so let's take a look at a couple of vector kind of checking your work, vector concept ideas for 2D momentum. All right, question 1. A 500-gram ball traveling to the right at 4 meters per second collides with and bounces off another ball. The figure shows the momentum vector of P initial of the first ball after the collision. Draw the momentum vector P2 of the second ball. Okay, so basically we need to figure out what's the momentum that will make this work. All right, so we have the vector first ball after the collision of the second ball. Okay, So traveling to the right collides with, yeah, so essentially we know that it initially was traveling entirely to the right, all right? So this is our P initial, all right? And then we know that we need a vector P2 that's going to add up in that direction, all right? So P2 has to be this same vector in order for this system to work, okay? Why is that, all right? Well, if we have a 500-gram ball that is traveling to the right at 4 meters per second, well, that's 2 Newton seconds, all right? So I know from this information, 0.5 times 4, that is 2 Newton seconds. Okay, so I know that's my initial momentum. And I know momentum has to be conserved, which is why I write P initial equals P final. Well, the only way for it to be conserved is have a P2 that with tip to tail vector addition gets me to P total or P initial. Because P1 plus P2 equals P final, which of course also equals P initial because the system has conserved momentum. Okay? So concepts there in terms of momentum conservation and the vector notation, the vector figure is there as well. All right, so a couple concepts you want to make sure you understand because this is if you understand this idea, you can save yourself so much trouble about not getting confused with your expectations or being able to check your work. Okay, so hopefully this makes sense. Let's do it again to make sure it makes sense. Okay, so all right, so here same sort of thing. I have a 500-gram ball. It's traveling 8 meters per second, 8 meters per second, and so that means it's longer. That means it's going to have a length of 4. Right, here's 2. This would be 3, and this is 4. It doesn't quite fit on the graph, right? But this is the initial momentum, also the final momentum. And then this, I know I have a P1, and then I know I need a second momentum vector that will add up to P initial. And that would be that one right there. That would be P2. And if I draw it with its tail at the origin, then it's just this right here. Okay? So I know that must be the case. So draw the momentum vector P2. Well, that's it. That's got to be it. All right? So those momentum vectors together have to come up. They have to collide to create that total momentum, okay? Because essentially, the initial momentum was the momentum of the system. After the collision, then that would also be the momentum of the overall system, of the two balls together, okay? So P1 plus P2 equals P final, all right? Hopefully that makes sense. All right, now let's go back to the algebra. Okay, so we're just going to continue with types of collisions, always starting with the same equations and just rinse and repeat, right? Let's do this a few times, okay? So example 2, we're on to the no more perfectly inelastic. Now we're on to partially inelastic. All right, so billiard ball A of a known mass, 120 grams. All right, it's got a known initial velocity. All right, strikes another ball initially at rest. Okay, so that's always a nice, kind of a simpler type of problem where one of them is at rest initially. All right, we do know the mass of ball B, 0.14 kilograms or 140 grams. All right, as a result of the collision, ball A is deflected off at a known angle of 34 degrees. Okay, so we know this angle to be 34 degrees. We also know the final velocity of ball A to be 1.85. All right, so what do we not know? Well, we don't know the final velocity of B or its angle. Okay, so those are our two unknowns. All right, so here I'm explicitly calling attention to them. I won't do this with every problem since it's kind of the first one we're doing like this. These are the two things we don't know. We don't know the two kind of final states of the ball. Now, another way to think about it, since VB is the magnitude of the final velocity, we could also think that the two things we don't know are actually VBX, write that more clearly, VBX and VBY. Because saying we don't know those two are the same as saying that we don't know the hypotenuse and the angle. All right? Because, not knowing two sides of the triangle is the same as not knowing, like one side of the right triangle and the hypotenuse. Okay? But here, I think it makes sense to say those are our unknowns and then go from there. We're going to use our momentum equation. Okay? In this case, we weren't told that it was elastic, and then in part B, we're asked how much energy was lost. So that definitely implies that kinetic energy is not conserved. So we do not have a third equation for kinetic energy because it's not conserved. Now, in a problem like this where it's not explicitly stated like that, you have to kind of reason it out, but really don't assume that the problem is elastic unless you're told it's elastic. All right, and here we're not told that it's perfectly inelastic or elastic, so it's probably partially inelastic. All right. Furthermore, as far as the glancing collision, this is a good example of a glancing collision because unlike with the peregrine falcon and the pigeon, where the velocities work with the things that were offset, here we can clearly see it's the center of the two balls that are offset. And that's why, we're not told exactly, what's the difference between their centers. We haven't even actually, in terms of the textbook, defined center of mass yet. We'll do that in another chapter. But hopefully conceptually it makes sense that if they hit like this, that they'll both go off at different angles. Okay? That's a glancing collision. All right, anyway, moving on. We'll just expand on our two momentum equations. All I've done here is just write them out in terms of their components. So for example, the initial momentum is incredibly simple, right? Because VA is moving entirely in the x direction. And so this is our entire initial momentum in x. And then our initial momentum in y is just 0, right? Because sure, after the collision, both balls do have y components of momentum because they have y components of velocity, right? Clearly. But they didn't start with any of that. So that means that these two have to sum up to 0, which is great algebraically, right? Because it means we can actually use this equation as a good starting point of solving our system of equations. All right? All right, so let's do part A, right? Which is just find these two unknowns. All right, so what do? So I'm going to write a new equation. The new equation here is just, it's going to be a combination of 1 and 2. Essentially, actually, it's entirely from 2. All I'm doing here is just isolating VB prime from equation 2. Okay? And so here, right, so I'm just, exactly. Okay? And then VA prime, there we go. So this arrow isn't specifically referring to this term, it's just referring to the whole thing. So 3 is just rewriting 2, all right? But I happen to number the equation just so you can see the process here, all right? And then what I'm gonna do is I'm going to then rewrite equation 1, right? Because you can tell this is equation 1 because look at the left-hand side, it's the same. Then look I've done. As I plugged in my labeled equation 3, which is of course just a rewrite of equation 2, I've plugged it into equation 1. So what I've done is I've replaced VB prime with this whole expression. Why have I done that? Well, because now I have a single equation with a single unknown. Because if you look here, what do I have, right? Well, I got VA prime, which I know, shows up twice. I obviously know VA, all right? And then I've got theta A prime, which is the final angle of A, but I also know that, right? So my only unknown is theta B prime, the angle, all right? Because that's what I need, right? I need a single equation with a single unknown. So then I can go ahead and then solve for, or at least isolate, theta B prime, the final angle of ball B. It ends up being cotangent because I'm going to have a sine over, or I actually have a cosine over sine, all right? And then I go ahead and just solve this for the angle, right? Just doing an inverse cotangent or taking the inverse of both sides if you don't want to do an inverse cotangent on your calculator. That way you can do an inverse tangent. But however you want to do it, I just solve for that angle, all right? So make sure you can do this work here, because here I don't show plugging in the numbers because I'm trying to kind of squeeze this one in. And so then with negative 39.2 degrees. Does it make sense? Yeah, it seems reasonable, all right? Okay. And then I can easily then back substitute that into equation 2, all right? And then basically, yep, just plug it into here. And really kind of more, actually equation 3, which is just a rewrite of equation 2. But when I plug that known final angle for ball B back in, I find out it's a velocity of 1.4. Okay, excellent. All right, and now you can then plug everything back in to make sure it works. Right, that's a key step. If you're really unsure about your work, plug them both back in. Make sure that those two with these values sum up to 0, and then sum up to this known value in Newton seconds. Okay. All right, in part B, it's very straightforward. How much energy was lost? Well, now that we know everything about the final and initial states, we just plug everything in. So it's just E minus, so this is just E final, or, yeah, so this is the initial energy minus the final energy. And the reason it's initial minus final is because this is energy lost, okay? So it's just gonna be the magnitude of the energy lost. If I did final minus initial, which is probably more typical, right? Final minus initial, well, that's gonna give me a negative because energy is lost. But here, since I know it's lost, I'm just solving for its magnitude. All right, and then so this is just the initial energy is super easy, right? Because it's just all the energy of the system is that of the ball A, that is, all right? Because ball B is of course at rest initially, and then afterwards we find MAVA prime, right? Which we already knew, we were given that, and since we solved for VB prime, we can just plug it in, plug in that 1.4 meters per second, plug in all our numbers, and we find out that we have 1.28 or 0.128 joules of lost energy. So again, it was a partially inelastic collision. All right? Okay, so algebraic steps there, checking for energy, definitely check your work, and doing some inverse trig, because often you're solving for a missing angle. All right, so let's look at another one. All right, so this one is elastic. So now we're on to type 3. Well, we'll go back and do a couple more examples, but now we've seen one of each type. So a proton traveling with a speed of 7.5 times 10 to the 5 meters per second, so really fast, but of course it's a proton, so protons move quickly. It collides elastically with a stationary proton. Okay, well, stationary is nice. That's going to make our system easier. One of the protons is observed to scatter at a 60-degree angle, should say angle. At what angle must the second proton be observed, and what will be the velocity of the two protons after the collision? Well, let's see. Okay, so zoom out a tad. So before, it looks kind of a lot like the problem above. Okay, the only difference is that this time it's elastic, right? We have one thing coming in. It's going to be a skewed or off-center collision, or a glancing collision. That's the term we're using, because obviously it has to be, because we're told that it scatters at an angle, right? It's not head-on. Okay, and so basically it's going to look the same as the example above, except, as I said, this time it's elastic. Okay, so let's go ahead and solve through. And that also means that we were given less information, doesn't it? What angle must the second proton be observed? Because we were just given the final angle. We weren't given the final velocity of the proton. We were given its initial velocity of the proton 1, but we weren't given the final velocity of proton 1, and we weren't given the final velocity of proton 2. So does that mean we have 3 unknowns? Sure it does. We don't know this, we don't know this, and we don't know that. Okay? So 3 unknowns. Okay? So that means we set up 3 equations. Yeah, I know, right? It's a bit of a bear. This is the only time in this class we're going to have 3 equations like this. All right? Luckily, at least one of them is at rest, so we can go through and look here. Our x1 is going to be just the initial momentum of the proton, and y, it's just 0. And then the initial kinetic energy is also fairly simple. All right? I cancel out m's because another good thing about this particular example is that they're identical protons, so all the m's cancel out. So just one less thing to kind of carry through. In the kinetic energy one, we might as well just get rid of all the 1/2s. Okay? Also notice that I'm keeping the kinetic energy in this form with everything squared. All students that will say, oh, didn't we have that nicer form of the kinetic energy where it's just the difference of the velocities is equal to, of the initial velocities is equal to the negative of the difference of the final velocities? If you recall from lecture 19, we used it a couple times to make our life easier when we were solving for specifically elastic collisions because it applied to conservation of kinetic energy. Well, no, that only works for head-on collisions. Okay, so the derivation that gives us that equation that I said we could use, was our kind of prefabricated equation, if you remember me calling it that. Well, that doesn't apply here. Okay, we have to just use the basic definition of kinetic energy. Okay, all right. So just use this. Okay, all right. So moving on. So what do we want to do first, right? Well, we want to think of just. It's always just kind of this. It only comes with practice, right? But you just have to look at the equation and be like, well, what's my first step? What unknown can I find easiest? Okay. Well, I look here and I say, okay, well, it seems like I can start to isolate theta, right? So I'm going to express cosine theta in terms of the 2 final velocities, because I don't know either of them, right? I don't know 1f or 2f. Okay. And then I'm going to do the same thing for sine theta. Okay. So I'm also going to express sine theta in terms of the final velocities. Why would I do such a thing, right? Well, kind of this, if you recall, right, this is another throwback. If you recall when I was solving those rather complicated problems for the banked turns with friction of cars, and we was like, oh, well, there's this general kind of strategy where you solve both the equations for the normal force and set the normal forces equal to each other. It's kind of the same thing here. By solving for cosine theta and sine theta in terms of both the unknown final velocities, well, then I can use a wonderful little trig identity called cosine theta squared plus sine squared, cosine squared theta plus sine squared theta equals 1, right? The most well-known trig identity there is. And now I've got a nice expression, okay? An expression where I'm able to relate the final velocities to each other, kind of just right away, all right? Well, 3 steps in at least, okay? And what's nice about that is then I go on, and I'm just going to continue to clean up this expression that came from trig, which came from solving for the two expressions of cosine theta and sine theta, okay? My one unknown angle, all right? And then I'm just going to continue to clean that up, all right? And then I'm gonna turn it into this, okay? So I'm going to get to this point, all right, where I've cleaned up the expression a bit, and then I'm going to notice that I know from kinetic energy that V2 final squared equals V1 initial squared minus V1 initial, or V1 final squared, okay? Okay, and again, this just comes straight from 3. It's basically what 3 tells us. And the reason I would even consider that is I notice that there's a V2 final squared right over here. Oh, that means I can get rid of it, all right? And now, what do I have? Well, now I'm going to have an expression with only a single unknown. Because check it out. When I substitute that in, then my only unknown is going to be V1 final, right? Because look, V2 final doesn't show up on the left-hand side of the equation. Okay, so I'll do that. Okay, all I've done here is just replace V2 final squared with this right, with the difference of the squares for proton 1, both initial and final. All right, and then cancel out this term because it's the same term on both sides. And then finally go in, all right, clean it up even more. All right, and then I do take note that there's a solution we're going to reject. We're going to reject that V1 final equals 0 because it is impossible. All right, V1 final is clearly in motion. All right, and so that particular solution to this expression, because essentially this is like the quadratic formula, that in fact it is, right? And we always reject one of our solutions, or often reject one of our solutions, not always, right? Sometimes both solutions from the quadratic formula do make sense. But here, one of the two solutions does not make physical sense, okay? All right, and so then we just solve for the other solution for V1 final, okay? So I'm just gonna see, and I'm saying it's like the quadratic because I got a squared term and a linear term, and V1 initial is known, right? We know, I've forgotten now, but we know it's 750,000 meters per second, or 7.5 times 10 to the 5 meters per second. Okay, so then we just go ahead and solve for it, right? Solving this is quite easy, and we get that it's 3.75 times 10 to the 5 meters per second, or 375,000 meters per second. That is our final velocity for proton 1. All right, so every one of these algebraic behemoths, which are a lot of these types of problems, they're always really tough until you find the first unknown. Because once you find the first unknown, and this might take you back to your pre-calc class, then finding the other two are way easier because you just back substitute and you're done, right? And that's going to hold true every time, all right? So we back substitute because we know that there's a direct relationship between V1 final and V2 final. It's right here. See, it's just the difference of the squares. I could literally just take the square root of both of these, right? And that's from equation 3. And so then we easily get that V2 final is 650,000 meters per second, or 6.5 times 10 to the 5, all right? All right, and that makes sense because again, it's the one that's going faster. It was at rest, right? Okay, and then finally we need to solve for this angle, all right? And to solve for the angle, we're going to go back to equation 2. This one right here. This is definitely the easiest one to solve for it, and just solve for our unknown theta, and we find that as 30 degrees. And we couldn't have done that initially because we didn't know V2 final, but now that we do know V2 final, we can easily solve for it. Negative 30 degrees. Okay, all right. So here's the thing, and here I denote it as negative. So really I'm saying that, that this thing inside is negative 30, okay? Not to double count the negative. And it turns out actually that I'm not gonna prove it, but it turns out whenever you have equal mass objects like this, and one of them was at rest, the sum of the angles will always be 90 degrees. So you can actually cheat and just say, oh, I already know that this is 30, all right? But here we're actually showing that indeed that holds true. It's not a proof, but we're showing that it holds true, okay? All right, so that's it. One more example down, okay? So here is the next one. So here we're going back to partially inelastic, because the reason that I jumped ahead and did I did an elastic was because that one was honestly a little bit easier than this one, and I wanted to kind of do them in order of complexity. So this one is a partially inelastic. That's kind of tricky because this is the type of partially inelastic where I specify how much energy is lost, which basically means that we can have a third equation because, let's read it, okay? So the mass of the puck initially traveling to the left is 20% greater than the mass of the puck initially traveling to the right. So here we're gonna have, again, a relationship between M1 and M2, kind of like in the last one with the protons, but in that case it was simple because they were just equal to each other. But here one is slightly bigger than the other. Before colliding, the pucks approach each other with momenta of equal magnitudes in opposite direction. So again, kind of interesting setup here. We're told that these two, it's a head-on collision, right? Well, at least head-on in the sense that they're heading towards each other. It's glancing because they don't just bounce off in opposite directions. The fact that they go off at angles tells us it has to be a glancing collision. In other words, their centers are not lined up. But we're told that they do have equal magnitude momenta, okay? Excuse me. And the right puck has an initial speed of 10 meters per second. Okay, so we know that this one has an initial speed of 10 meters per second. And we're asked to find the speeds of the pucks after the collision if half the kinetic energy is lost during the collision. Okay? All right, so let's think about that. What do we know? How are we going to find things out here? All right, so let's simplify it, right? We are only solving for two unknowns because we're just going to find both their speeds. Okay, we're given both the final angles. So even though we kind of have three equations here, it's what's called an over-resolved system because we don't need all three equations because we don't have three unknowns, but it still is going to be useful to have all three. Furthermore, we are told that their initial momentums are equal in magnitude. So if we look at the x direction, the momentum in the x direction, we know that m1 v1 initial, that would be this, the momentum resulting from this right here, this mass and that velocity, has to be equal to m2 v2 initial, so they have to cancel out because they're opposite in direction, and momentum is a vector. So that means that the left-hand side of our x momentum equation is the same as the left-hand side of our y momentum equation. They're both going to have zeros on them. So that's going to be nice, okay? And then we're going to have a bunch of final velocities that we don't know, okay? So let's see what the process looks like, okay? So first of all, I'm going to set P1 initial equal to P2 initial, all right? I'm going to do that because I know that there's a relationship between their masses. I was told that, that P2 initial has a mass that is 1.2 times greater. So in other words, M2, this right here is M2, all right, M2 is equal to 1.2 times M1. So I'm going to use that to cancel out M1 because we were never told what the mass was. And then that's going to allow me to solve for V2 initial because I was told that V1 initial, that's this one, was 10 meters per second, recall? But we were never actually told what V2 initial was. But we can easily find it. It's 8.3, okay? And of course, it's 8.3 in the negative direction, so it's negative 8.3. But here, I'm just solving for its magnitude, okay? So V2 initial is 8.3, all right? Cool. That's going to be helpful. It's good to know that number, okay? Now we're going to go ahead and find V1 final x, all right? So that's going to be the final velocity of this one after the collision. So essentially, it's this arrow right here we want to solve. All right, it's going to be m2 over m1 times v2 final x. Okay, so just times this one. All right, and we're just getting that right out of our momentum equations. Okay, and specifically our x momentum equation because everything's an x. Okay, so this expression right here is coming right from that one. Okay. So then I'm just going to write it out in terms of the actual components. So V2 final x is V2 final times cosine of 30, because again, we know both angles, so hey, no inverse trig, right? And then we do the same thing for y, all right? And then I'm going to rewrite this, because m2 over m1, by the way, is just 1.2, because the ratio ends up being exactly 1.2, because m2 is just 1.2 times bigger than m1, okay? We're kind of given an odd amount of data in this one, okay? So I think just kind of parsing out what was given in the problem is almost the hardest part of this example. All right, and then we go ahead and write that out because again, it's just the y component. Okay, and then kinetic energy, we've got this here. Okay, and so this is just telling us that v1 final squared, okay, is going to be equal to v1 final x squared plus v1 final y squared. Okay, all right. So then the kinetic energy becomes. All right, let's see what it looks like. So we know that the final kinetic energy is half the initial kinetic energy, which I wrote here as one of our kind of initial setup equations. All right, and so then we're going to go ahead and plug in for our final kinetic energy, or actually here, let's do it like this, show the whole thing, okay? So this is going to be, over here we have, this is our final kinetic energy and our initial kinetic energy related to each other. We can see the final is all over on this side, so I kind of swap sides. So this is all the final, all right? And then everything everything in terms of the initial kinetic energy is over here. Okay, and all right, then we're going to go ahead and simplify this expression. All right, and okay, so I'm just going through and simplifying it. All right, until finally we have a relationship between V1 final and our V1 initial and V2 final. All right, and look at this. This only has a single unknown. In fact, we only had a single unknown as soon as this step above. All right. In fact, I should even specify it as soon as the whole purpose of writing this was to show that then when we did the kinetic energy, we would have an expression with only a single unknown, which is just V2 final. Okay, because we know V1 initial and we know V2 initial for that matter, right? We know V2 initial is 8.3. All right, so we can then solve for one of our unknowns, V2 final. And there it is, right? In terms of kind of not putting a decimal, putting it as a square root of a fraction, and then finally plugging it in relative to our known initial velocity of 10 meters per second, and it's 5.89. Okay, and now of course finding v1 final will be much easier. All right, we can find v1 final by just using this equation again. All right, and then that one's going to be just 1.2 times v2 final, or 7.07. All right, there's our two final velocities, okay? And that's for a case where half the kinetic energy is lost. Does that make sense? Well, we can plug it back in and check. And indeed, we'll find out that it does exactly match up with the half of the kinetic energy being lost in this particular collision, right? So because that helped specify the values. Okay, so hopefully this makes sense as a type of partially inelastic collision where the actual amount of energy loss was specified rather than being asked for. Okay, because a lot of times it's like, well, how much energy was lost? But here I told you how much energy was lost, and that helped you solve for unknowns. Okay, all right, well, let's carry on to our final example. Okay, so this one is another elastic collision. So this is going to be the full three unknowns. This is the only other example other than example 3 that has 3 unknowns. This one also is a bear. This one's really hard to solve. This is tricky enough in terms of the algebra that I wouldn't give it to you on an exam, but I just wanted to show you that no matter how hard they are to solve, you can always just go through and just do the algebra and find a way to solve them. Now, the reason I wouldn't give it to you on the exam is because honestly, solving it by hand this way, using kind of, substitutions of equations and just going through, it's a clunky way to solve it. I mean, really, when they get this complex, we'd be better off using something called linear algebra or using a computer to solve them. And so just, I think that although it's good to show it's possible and it's solvable and it's kind of a fun puzzle, it's just not, the main focus of the class. But let's just show that it can be done. All right, so a two-particle elastic collision is shown below, occurring in the origin of the XY coordinate system. So the collision takes place right there. We know that mass 1 is 6.2 kilograms, and it overtakes the slower and more massive M2 because essentially they're both moving in the same direction initially, as shown by the green and pink arrows. All right, so the initial velocity of particle 1 we know is 4.3 meters per second, and its final velocity following the collision is 4. Okay, so it slows down a little bit. All right. And it's a glancing collision, so the angles following the collision of the two particle trajectories are 56 degrees for 1. So this particle, M1, gets bounced off in the kind of positive y direction, and an angle of 56 degrees relative to the x-axis. Meanwhile, M2, which we haven't specified anything about so far, it gets bounced downwards, because remember it was the one that was at rest. It gets bounced down at 87 degrees. Okay, so what do we not know? What are our unknowns? Well, I ask M2, V2 initial, and V2 final. Okay? So, all right, so that's the thing, is we don't know its mass. We were told it started from, what do we know about it, right? All we know is the angle that it gets bounced at after the glancing collision, and we know that it started at rest. But we don't know how massive it is. We don't know, actually it wasn't at rest. That was the thing, right? So it was in motion. Of course it was in motion. It was overtook by the faster one. I think I just said rest because I'm used to it when putting them at the origin, they're just sitting there waiting to be collided with, but this one's not. That's what makes it harder here. It's in motion, it's just moving more slowly, which is how M1's able to catch up with it, and where it catches up, we just happen to call the origin because we might as well, okay? But anyway, so it was in motion, but we don't know how fast. We know it's gonna be slower than 4, because otherwise they never would have collided, okay? And it is, okay? And so that'd be a good way to check the reasonableness of our values. But we don't know the final velocity in magnitude either. But we do know its angle, okay? So it's kind of a weird set of things we don't know. It's like M2 is a mystery particle. It got lost. And this is actually really relevant. A lot of physicists' physical experiments are based around mystery particles and momentum like this. And so, we're trying to reason out its mass and both its initial and final velocities, okay? And that ends up being just a really tricky set of things because all 3 of the equations are all going to have unknowns that don't have easy steps to kind of work out. But let's write them down, okay? So this is going to be just like example 3, conservation of momentum x, conservation of momentum y, and conservation of kinetic energy, okay? One of them 0, luckily, at least, right? Their initial momentum y is 0, all right? But still, how do we actually end up solving this, okay? So one of the first things we want to do is express M2 in terms of some other unknowns, okay? Because we don't know M2. We do know M1. We do know V1 final. We do know theta 1 and theta 2, but we don't know V2 final. So it's not like we can just find M2, okay? This is going to be helpful. We're going to be able to use this for substitution purposes, but again, this is not a single equation of a single unknown because there's 2 unknowns, which I underlined. All right, well, let's carry on. Let's rewrite momentum in x, and I'm going to go ahead and substitute in for each M2 this expression here. At least that way we'll have an equation with fewer unknowns, all right? So let's think about it. Have we finally reached our goal of having a single equation of a single unknown? Well, I've got V1 initial, which we know. We don't know V2 final, but here's the other thing. We don't know V2 initial. So I've got a V2 final and a V2 initial, so this is still an equation of 2 unknowns, all right? Well, I certainly would not have wanted to substitute in the kinetic energy equation because everything's squared, first of all, which makes it tricky to deal with, and also that wouldn't have solved our problem because we still would have had an equation of 2 unknowns. So there's no kind of quick path to having a single equation to a single unknown. So instead what I'm going to do is I'm going to use this big old equation to at least express V1 in terms of V2. Or let me say that in a way that's actually accurate. Express V2 final in terms of V2 initial. Okay, so express the final velocity of V2 in terms of the initial velocity of object 2. Okay? All right, so I'm going to go ahead and just start isolating the initial velocity of object 2. Okay, this one right here, our mystery object. Mystery because we don't even know its mass, right? Okay, and so I just do, this is now just a bunch of algebra collecting like terms, factoring things out. All right, so make sure you can get from that step to that step. All right, and that's not too much went on. I basically just factored things out and isolated V2 initial. All right, and one thing I did is I cross multiplied by everything that was attached to V2 initial, because this is the only V2 initial term. So I just cross multiplied by this business onto each of the other terms. Okay, and that's how you get this. All right, and then clean it up a little bit. All right, that's all I've done here. Clean it up, and then I actually plug numbers in. Okay, because we know, again, we know both the angles, and we know both the initial and final velocities of particle 1. Okay, so plug everything in, and so then what we get is we get that the final velocity of object 2 or particle 2 is equal to 0.569 times its, or the initial velocity is equal to 0.569 times the final velocity. So this is nice because now we have a real simple numerical relationship between the two. What are we going to do with that? We're going to plug in the kinetic energy, okay? And so what I'm going to do is I'm actually going to denote, so I can keep this in terms of, I want to keep it sort of symbolic looking. I don't want to have a bunch of numbers that I'm multiplying all the time. So for clarity of solution, I'm going to call this value, this coefficient, because it's dimensionless, right? Look, it's clearly dimensionless, as you can see, because it's just all angles and a ratio of velocities. I'm just going to call it gamma, okay? And so then what I'm going to do is then I'm going to say that V2 initial equals gamma, which is just 0.569, times V2 final. Okay? And now I'm going to substitute that into our kinetic energy equation. Okay? So that's what I'm doing here. I'm also replacing M2 with this expression here. Okay? And here's the whole kinetic energy equation. Why have I done that? Well, now I finally have it. I finally have a single equation with a single unknown. All right? My only unknown is V2 final. All right? And then when I simplify it and solve for it, I isolate it. It actually isolates pretty nicely. Again, there's just a lot of algebraic footwork to go from this step to this step. All right, and again, this gamma is just a number. It's just 0.569, okay? And then plug in all my values, including the coefficient I solved for, my gamma coefficient. All right, and there we go. We finally have one of our unknowns. V2 final is 1.11. And now that we have that, it's going to be super easy to find the other two things. All right, so we'll back substitute. Oh, yeah, really easy, first of all, to find V2 initial, because we know that V2 initial is just going to be about half of that. All right, and again, it is. We get 0.631. All right, and then finally we can find the mass. All right, so finally the mass, and there we go, 18.6. And again, that's what made this so tricky, was not knowing the mass. That's why it was so hard to work it out. And there we go, our mystery mass, 18.6 kilograms. That made those particular angles possible. Okay. All right, so again, there'd be better tools than just doing it, through substitutions like this, but it's totally doable, and hopefully the idea, the process, the fact that we always start with either just these two equations for partially inelastic or perfectly inelastic, or all three of the equations for elastic, that holds true, and you can see that there really is a process to doing these type of glancing collisions. Well, thank you so much for watching this lecture video, and I will look forward to some more. Bye for now.